Hello, in this lecture we will start seeing how to write a decoder for LDPC codes in the 5G standard in MATLAB. Okay, so I am going to write a quick and small MATLAB script for doing the decoding. Once again, remember, we are not going for very optimized code and very efficient implementations, just to show you how to write a decoder, number one. Okay, so in the previous MATLAB coding exercise, we saw the encoder. I loaded the base matrix, and hopefully you still remember all those things. You have the base matrices in a folder, and then you know how to load it and all that. So let me quickly remind you on how that works. So let me go to the MATLAB window. I need to go to the correct directory. Okay, so this is my folder in which I do my coding. You can see this subfolder called base matrices, and one can load base matrices NR. There are a whole bunch of parameters. You remember, the first one is the base graph number, next one is that J parameter, and the last one is the expansion factor. So let us pick up 1016. I mean, you could pick up anything, so we can pick up that. So that is the base matrix, and for convenience I like to store it in B. Okay, so if you look at size of B, it is 46 by 68. You remember, it is if you just look at B, okay, so B is a little bit difficult to look at. Maybe you can look at the first three rows of B. Okay, you can see a whole bunch of minus ones. So if you scroll up a little bit, you will see the other numbers. Okay, so the first few columns have some numbers. Remember, the expansion is 16, so you will have numbers from -1 to 15 in the base matrix, and we know how this is, right. So if you look at the number 10, you take the 16 by 16 identity matrix and shift it right by 10 positions. Okay, so this is the base matrix, and this is expanded to form the parity check matrix. Okay. So starting with this base matrix, we are going to work, and we are going to start building a decoder. Okay, so let us move to the MATLAB editing window. This is the encoder, and maybe we need the 7.4 Hamming code. Okay, so this is the BPSK 7.4 Hamming code. I am going to save this as BPSK NR LDPC. Okay. So we can pick an EB over N0. I will pick 4. The rate is sort of difficult to determine. So what we can do here is we can repeat what we did before. So you load base matrices. So remember, now I will have to run it from my correct directory. Base matrices and NR 1016. I think that is correct. Let me check that once again. So that is the command we ran. 1016, right. So that is the thing. So that is okay. We loaded that. Okay, and then we set B to be equal to 1016. So now I will have my base matrix in this B, and now I am ready to find out what M and N are. So I will have I need the size of B. I will use this. So we know what MB is going to be, right. So MB is going to be 46, NB is going to be 68, right. So that's this NR 1016. If I change it to something else, this will change. Okay, and also clearly Z, which is the expansion factor, is 16 here. Okay, so once I do this, I will be able to determine these things. Let me put this a little bit forward. K equals NB minus MB times Z. This is the number of message bits, and the number of code word bits. So usually when you generate the code word, I am going to generate the entire code word, and we will simulate that in this code. But typically in wireless standards, people do something called rate matching. So you will do some puncturing, you will do some shortening, a combination of these things, and put it into some circular buffer and read from that, etc. So all of that we are not going to do in this lecture or in this class. We will just assume the whole base matrix and the whole parity check matrix is what we simulate. Okay. So later on, maybe if we have time, I'll go through some examples where maybe I show you some puncturing, but it's quite easy to program the puncturing part, or at least I'll mention how that is accommodated. Okay. So n, as far as I'm concerned, is nb times n. Okay. So remember once again, this is mb is 46, nb is 68. So the difference is 22. So k will be 22 into 16 and n will be 68 into 16. Okay, so that's the current thing I'm working with. Okay, so the rate is going to be k by n. So this is clearly not the Hamming code. So oops, it's going all over the place. I just want to delete it, but okay, let's just do it. Okay, so once you do this, you have your EB over N naught, you have your base matrix, you have the rate, so you can find your sigma. Okay, so there's no way I can list out all the code words, so that part is completely not needed. Okay, so the other parts of the simulation will remain the same. You'll generate the k-bit random sequence, and then you start encoding. So now remember, I want to focus on the decoder. I don't want to be stuck with I'm just testing my decoder in some sense, right? So I don't want to be doing a lot of blocks. I'll just do one block, and I don't really want to be encoding. So I'm going to comment this out. I'm not going to be encoding, and what will I do instead is I'll simply assume the message is zeros. Okay, so I'll transmit the all zero code word always. Okay, all zero message and all zero code word always. It turns out that's enough for decoding checking. Of course, in the decoder I won't assume all zero code word is being transmitted. I'll try to decode it based on the received code word, and this way I bypass the encoding requirement. Okay, we know we have an encoder, we could program that in, but that just adds the complications. We can do that later on. For now, I'm going to assume all zero code word. Okay. So you know, all of us know when all zero code word is encoded, you get all zero messages encoded with any linear code, you're going to get the all zero code word. Okay. Okay. So this is something we do for simplicity in the decoder. Okay. So after that, things are okay. It's exactly the same, nothing much to change. We're not going to be doing hard decision decoding. We are going to be doing soft decision decoding. In fact, this is going to be soft decision, iterative, message passing decoding. So all of these things don't apply. We'll have only one message cap, so this should be good enough. This is counting errors, right? So let me put that as counting errors. So now all that remains is the decoder. Okay, so hopefully you've seen I've got the setting completely done, everything else is fine. I only need to figure out the decoder. Is that okay? So I've loaded my base matrix, I've loaded my expansion factor, I've encoded, and I have my received vector, and I have to do my decoding. Okay, so all I have to do is decoding. It seems simple enough. Okay, so in the decoder we know it's iterative, so you need to figure out number of iterations. So maybe that's the parameter you want to set. We could set it here. Max iterations equals I don't know, we'll put 8. Okay, doesn't matter what you put here. So that's the max iterations. Okay, so we'll keep that. We'll use it when we have to. So now the iterative message passing decoding. If you remember, we're going to do layered decoding. So let me layered. I'll add that. Okay, if you remember layered decoding, we have one total belief vector which is initialized to R in the beginning. Okay, so that is my L. Okay, you can go back and look at the slides if you like to see where this notation is coming from. I did a toy example with L being the total belief. Okay, so now that is set as R, which is the received vector. Okay, now I'm going to start working with R, right? So you remember I'm going to process one layer at a time, and for me one layer will be one block row in the base matrix. So you remember my base matrix has 46 rows. I'm going to take the first row and process it. Okay, I'm going to treat the first row as my first layer. Okay, so I'll process that and then add to the total belief and proceed. Okay, so that's what I'm going to do first. Okay, so L equals R, and then I have to start doing the first row. So how do I do the first row? So if you remember, B is my base matrix. It has a bunch of minus 1s, okay, and those minus 1s are not very relevant for me. I just have to go through and find out where the non minus 1 values are, okay, and then based on that do my row processing, right. So that's how it works. So it's you can do a lot of efficiency into this. Once again, I'm not going to worry too much about the efficiency. So the outer loop, the biggest outer loop will be the number of iterations. So I'll have ITR be equal to 0 is this iteration number, okay, and I will also have so there are various ways to do these things. So one can put a loop here on while ITR is less than max iterations, right, and end it, okay, and then overall I'll have ITR equals ITR plus 1, okay. So you might ask me why I'm not doing a for loop. So it turns out I might want to terminate in the middle if I have a valid code word as the answer. So that's why I like a while loop here. So this is my loop for the iterations, okay. So I will repeat for every iteration a certain the row processing steps, right. I'll process all the rows. So I put a loop for the iterations, okay, and then inside this iteration I'm going to process the parity check matrix, and there are multiple layers here, and each layer I will need a loop as well, okay. So that's going to be I'll call it layer equals 1 colon MB, right. So that's my number of layers, and that ends there, okay. Once again, what is L? L is my total belief, okay. So a lot of people will call belief as log likelihood ratio. I'm just using a slightly more generic terminology here. If somebody says L is a log likelihood ratio, technically it's proportional to the log likelihood ratio. There is a 2 by sigma squared factor there, so that's why I'm calling it belief. You can use LLR as well. I mean, it's not wrong. It's quite reasonable to say that, okay. And what do I do in each layer? In each layer I have to do row processing, okay. So it turns out most people like to do this in parallel. So one can do that as well, and we will do some sort of parallel effort here. So remember what's going to be each layer. So maybe I should take out this thing. So if you look at each layer, so the base matrix B, base matrix, and specifically the first row of base matrix, we saw that here. Maybe I should just do B of 1 comma 1 colon 9 or something, okay. So that comes in the first row. So you see the first row is 10, 5, 2, 15, minus 1, 4, 10, minus 1, minus 1. There are lots of minus 1s, but that's 10, 5, etc. So let me just copy this over to that side. So I mean, I don't need it to be exact, just for rough purposes. 10, 5, 2, 15, minus 1, okay. So you had 10, 5, 2, 15, minus 1. Remember what is 10? 10 is 16 by 16 identity shifted right by 10 columns, right. So rotate shifted right by 10 columns, okay. So it will have something like this, right. 10 would mean a little bit more here, okay. So something like that. So this would be this block, and then the 5 would come. 5 would be probably longer here and then shorter here, okay, and then 2, etc. Okay. So the actual parity check matrix is expanded from here, and there is some shift going on here, okay, and that's number 1. Number 2, if you remember, for every entry in the base matrix I need a storage matrix, right. So that's the message that's being exchanged. So that storage matrix actually needs to be for the expanded version, right. So I need a fairly big storage matrix to work with, okay. Without the storage matrix things are not going to work, okay. So that's the next big thing that we will define carefully now. Okay. So, how will you define the storage matrix? It needs to go outside of this. We can define a storage matrix based on B. Okay. And how is the storage matrix going to work? And remember, I do not need storage for every entry in B. B has a lot of entries, 46 by 68, but quite a few of them are -1s. Okay. For every -1, I do not need to store anything. Only if it is not -1, I need to store something. Okay. And how much do I need to store? For every entry, non-1 entry of B, I need to store 16 values, right. So, that is the expansion by 16, right, and it is only identity. Okay. So, 16 ones are there for every entry in the base matrix, or more generally Z ones are there for every entry in the base matrix. Okay. So, I have to find out how many non-1 entries are there, where they are, and well, sort of where they are is maybe B will give me, and wherever I have a non-1, I need to store 16 values. Okay. So, I will store 16 values in a sequence, and then we will have to do some rotation, etc. We will come to that when we deal with this, but for now let us declare this storage array. Okay. So, that is quite important, we need to do that. Okay. So, how do I do this? So, first I would need to find number of non-1s. So, I will call it slen equals length of, or I mean you can even do this, sum of B of colon not equal to -1. Okay. So, this is going to give you a total count of number of non -1 in B. Okay. So, why did I do colon? I just wanted to make it into one vector so that I can do this quite reasonably. So, you can get that, and then once you have slen, you can define your storage. Okay. So, my storage, I am going to call it R. R is zeros for now of slen comma Z. Okay. So, this is the storage for row processing. Okay. So, hopefully you agree that this is correct. So, maybe we can run up to this and see what the value is. Evaluate selection. If you do that, you will see what slen is. Okay, it is 316. Okay. So, even though there are, so if you remember, B is, if you do MB times NB, you get 3128. That is the size of the total number of entries in B is 3128, 46 by 68, but out of that only 316 are not -1. Okay. So, and you need memory only of that length, 316 times Z. Okay. Why is that Z? Because it gets expanded by Z, and that many ones are there in the final matrix. Okay. All right. So, that is good. So, we have done that, we have this R. Okay. Now, this R is sort of like a linear entry. So, for every non-1 I have R. Okay. So, let me show you why that is important. So, the storage for this, okay, storage for this will be R of 1 comma 1 colon 16, right. What will be the storage for this? That will be R of 2 comma 1 colon 16, and so on. Okay. And this will be R of 3, R of 4, and then there is a -1, and if you remember the matrix B, okay, there was a -1 and then there is 4, 10, -1, -1. Okay. Let me go to that once again. After -1 you have 4, 10, -1, so on. Okay. So, this will be R of 216, the storage corresponding to this will be R of 3 comma 1 colon 16, the storage corresponding to this will be R of 4 comma 1 colon 16. There is no storage here corresponding to -1, and the storage corresponding to this is R of 5 comma 1 colon 16, and so on. This will be R of 6 comma 1 colon 16, and so on, right. So, it will proceed like this. So, okay, so I should be, so hopefully that is clear to you. So, so this is how I am going to organize my storage. Okay. So, it goes row wise, okay, and wherever there is a -1 I will just skip that index, I will go to the next index in this. Is that okay? Hopefully that is clear. Okay. So, once again remember, my storage is just linear, I'm storing z values for each non-zero and non-1 entry in the base matrix, and it just goes linear. As you traverse row wise, I will go next memory, next memory, next memory, like that. Okay, keep that in mind. So that's number one. So as I process the first layer like this, I know what to do, right. So I come here, I have my storage. So I have my access to R. I have the L, the total belief corresponding to this. Remember, the L will come out, L is there, right. So that is just for the whole NB into Z. Okay, so you will have the first 16 and then the next 16, so on. Okay. So, you will have the first 16 L's corresponding to this, the R will be 1 comma 1 colon 16, but remember there is this little bit of shifted thing there, right. So, one needs to pay attention to that when you align it with the row, but as far as columns are concerned, it is the same. Okay. So, I am going to subtract. So, you remember the row processing, I do L minus R first, okay, that is the subtract operation in layered decoding, and then you do the row processing. Okay. There you have to align with the rows and then do the row processing, and then the L minus R and the new row get added to get the new total LLR. Okay. So, that is the operation that we have to do. So, we will do all of that. So, one needs to exercise some care when we do this, nevertheless hopefully it is easy enough to remember. Okay. All right. So, that is the picture here. So, hopefully this is clear to you. You have the total belief L. Okay. So, you have the total belief here L, which is in one vector, and then you have this R matrix which is storing sequentially as you go along the rows what your R value is. Initially it is all 0, but still you should store that, and then you do then you have to do row processing. Okay. Row processing involves L minus R, that is the first step. Next minsum row aligned. Okay. So, you have to do a row alignment here. Remember, why do I have to do a row alignment? Hopefully it is clear to you, because so while R starts like this, that is not aligned in the same row. Okay. So, the first thing is what is aligned. So, you have to shift by 10 and then only you will get the alignment in the row. Okay. Those are the corresponding things that you have to work with. Okay. And the final thing is L minus R plus the minsum value. Okay. Minsum updated value. Okay. So, this is what I have to implement, and there is this row alignment which I have to be careful about. Okay. So, to actually do the row processing, I like to sometimes pull in the values from the storage into some temporary storage that I will have, and then work with that. Okay. So, there are various ways to do that, and one so this is also makes sense, because usually the storage is in some when you actually implement, let us say in hardware, the storage is in some memory, and you want to pull it into some registers into a small operating unit and do the calculation and then write back into memory. So, this is something that you want to do to make sure things work cleanly. So, I am going to use some registers, temporary storage, for pulling in these this R values. L is okay, L is just available to me all the time. The R values I am going to pull from the memory into my sort of some temporary storage, do the processing and then store it back. Okay. So, that will be my flow. Okay. So, let us see how to get this done. Okay, not getting the right thing. Okay, there you go. So, I need to define that also. Okay. So, how many do I need? So, for that I need to know the maximum number of ones in a row, okay, in the expanded base matrix, or maximum number of non minus ones in the rows of B. Okay. So, for that one can write a small piece of code. So, if you look at B not equal to minus 1, this will give me a matrix. Okay. So, it is tough to see that. So, if you add up B not equal to minus 1 comma 2. Okay. So, this will give me the row weights. Okay. So, if you want, I can define this as row weights. Okay. If you did not believe me, you can look at the size of row weights. it will be 46 comma 1. So, there are 46 rows. So, in fact, I do not need all the entire row weights, I can simply do max of sum of b not equal to minus 1 comma 2. Okay. So, there are 19 that is the maximum weight that you have in this matrix. Okay. So, that is the number there. So, one can do that also. Let me define the temporary storage. I will call it T-reg, temporary registers, okay. Zeros of max of b not equal to sum of b not equal to minus 1 comma 2. I do not think I need this number anywhere else. So, that is why I am not worrying too much about it, comma z. Okay. So, this is the storage, register storage I will call it, for row processing. Okay. So, all the row processing I will use T-reg for. Okay. So, let us do that. Okay. So, now I come to the layer. So, I have to now read the storage, the R storage into my T-reg. Okay. So, it also depends on what layer I am in. Okay. So, there are various ways to do this. So, inside a layer, I am inside each layer. So, I will have to keep a count on where I am in R. So, I will keep that also as R count equals, I will call it a simpler notation, Ri equals, we will have just 1, does not matter. So, this is register storage for Minsum, that is good to have. So, let us go through. So, I am going to go through here for each layer and for each column in the base matrix. I am checking if that is minus 1 or not. If it is not minus 1, I can store it into my register, but I will store it after doing subtraction and taking care of the index also. So, let me do this a bit more carefully. So, I will call it Ti equals 1, and then if it is not minus 1, my T-reg of Ti comma colon equals, I need to do a mul shift of R of Ri comma colon comma B of layer comma column. Okay. So, I am shifting it and store, and what should I shift? I am not R, I need to do L of the column is 1. So, it needs to be col minus 1 multiplied by z plus 1 colon col into z minus Ri, and then comma this. Okay. So, let me just go through this. I just typed out a lot of things. So, you can see what I am doing here. I am taking the corresponding L. From L, if I am at column COL, then L of column minus 1 into z plus 1 colon column into z is the corresponding block of total belief from the entire L vector. And then what is my R? That is R of Ri comma 1. So, Ri is my index in the message, the storage register for the row processing, and there I take the Rith one, but after I subtract, I need to shift it. The shifting is to row align. Okay. So, that is the mul shift that we had even in the encoder, we saw this operation. I am going to shift it by the entry in the B. Okay. So, there is one step, let me do this, but then after I do this, I have to increment my Ti and then increment my Ri. Is it okay? So, once I did this, I have gotten all the values from the storage for the row processing into my registers for Minsum. Okay. Hopefully, go through this once again. For every layer, I am looking at every block column and I am seeing if it is minus 1 or not. If it is not minus 1, I have to process it. What do I do? This step actually does subtraction and row alignment. Okay. So, it brings in the corresponding value from the row processing, row storage R, and the corresponding value from the total belief. It subtracts the two and then shifts it by the actual value in the shift in the base matrix, and then stores it in T-reg. Okay. So, now at the end of this loop, once I am done with every column here, I have all the values brought into this T-reg register, and they are all nicely row aligned. Okay. So, now I am ready to do minsum. Okay, minsum on T-reg. Okay, on every entry in T-reg I have to do minsum, and that is I will just call it I equals 1 colon z. Okay, I have to do minsum now. Okay, so so doing minsum you can do in various ways. I am doing a simple loop here. You can do it without loops also if you like. I am going to do it just for simplicity. I am going to do it with loops, and just for okay. So maybe this is slightly, maybe we will keep it as 0 here just for I will do this in a slightly reverse way. Okay. So, this is better because if I start at 0 and add 1 before doing this, then I know Ti is the total number of non-zero entries at that point. So, I do not have to worry about that. So, Ti will be my total number of non-zero entries. Okay. So, Ti, this is Ti cross Z. Okay. So, there are Ti values, and for every value and in every it is all aligned nicely. So, I just have to do the row processing. Okay. So, how do I go about doing this? So, that is clear. So, I need my min 1 and min 2. So, I will set min 1 to be infinity, min 2 to be infinity. MATLAB allows me to do that. This is a large number. Okay. And then I will just process. Okay. So, how do I process? For j equals 1 colon Ti, and we can end it. So, loops actually are quite slow and bad in MATLAB. So, you should try to not use loops, but I am just using loops for simplicity. So, maybe we can avoid this loop here. So, let us try it directly. Okay. So, now I need to find, so remember I am processing the ith, so T-reg of colon comma 1 colon Ti comma I. Okay. So, the ith column in T-reg is what I am processing. Okay. So, I have to find the minimum value among absolute minimum value in the ith column of Ti, and then the second absolute minimum value, then the product of the signs, and then I flip based on that, right. So, that is what happens. So, I need to find the min, not only the min, I also need the position, right. Pos equals min of ABS of Ti T-reg of colon comma I. Okay. So, this gives me the first minimum. Is that okay? So, the first minimum, I don't know why is this complaining about I. Oh, okay. So, I will make it I1. So, it looks like I have used another index for I. Oh, there is an I for the I blocks. So, all right. So, I1 is something, okay. So, this is the first minimum, absolute minimum of course. So, now I am ready to find the second minimum. For the second minimum, one should not use the value in pos. So, min of ABS of T-reg of, I am not supposed to use the first value. So, 1 colon pos minus 1, and then pos plus 1 colon end, not end colon Ti. So, needs to be careful here. Let us not use 1 colon Ti, it is very important, comma I1. Okay. So, this should give me the second minimum. We will check it out. If I made a mistake, we will correct it. So, this should give you the second minimum. Okay. So, the first minimum and second minimum are set, that is very nice. But then what about the sign? The sign is I need this parity I can take the product of sign of T-reg of 1 colon Ti comma I1. Okay. So, that is parity for you, and then one can start so, it is good to keep the signs also. So, maybe what I will do is I will store the signs separately, I call it S. These are the signs, product of S is the parity, okay. And then T-reg of pos comma I1 equals min2. Okay. So, I am setting wherever the minimum was, I am setting the second minimum T-reg of so actually it is better to do this in the right way. First do min T-reg of 1 colon Ti comma I1 equals min 1. So, do the absolute minimum, and then the position alone you replace with min 2. So, this is a slightly easier way to do it. And what about the signs? T-reg of 1 colon Ti comma I1 equals S prod parity times S dot into T-reg of 1 colon Ti comma I1. So, first we assign the absolute values, okay. So, assign min 1 to everything, and then the first minimum position gets replaced by min 2. So, at this point only absolute values are there, and then we assign the signs, okay. Okay. So, hopefully this is clear enough. Remember, once again we did the subtraction and row alignment and stored the values in T-reg, and now we just have to process the values in T-reg for minsum operation. How do we do this? We take the Ti values and do minsum on each of those values. Okay. They are already aligned now, so we do not have to bother with aligning here. We just do for each of the expanded expanded rows, we do minsum. Okay. After you are done with minsum, you have to write back. Okay. So, column alignment and store in R. Okay. So, for that there is an addition also, column alignment, addition and store in R. So, one needs to be a little bit careful here. Remember, see when we did the subtraction, the subtracted values okay. So, we did row processing on the subtracted values, but then after the row processing we should not be adding it to L, we should add to this. So, one of the things to do here is which I did not do, is the assignment of the subtraction. So, I think it is good to do this. Let me so this is important. We need to do this. And so, once you subtract, you do not have to subtract again. Okay. So, this is nice. Okay. So, we did subtraction and then row alignment goes here. Okay. So, this is pretty clean. So, our total belief has now been subtracted with R, and then we stored it in we did a storage in the T-reg, and then we did minsum. And once we did minsum, we can now add, okay, column align, add and store back in R. Okay. So, I think this is the layered decoding algorithm. Hopefully, this part is clear. So, I was not doing the subtraction and storing carefully. So, I think this should be okay. All right. So, now we do the column alignment and add, and this needs to go on for every column, right. So, this will go like that. Okay. So, I think this is fine. Okay. Okay. So, we will do the index again. So, Ri is going to be Ri minus Ti. Okay. Start back at the first index. Ti, do I need Ti to go to 0? Let me see this. For column equals 1 colon NB, and if B of layer comma col not equal to -1, then you can do something here. So, what do? I need to align according to the column, then add it to L, right. So, that is the important part there. So, R of, so Ri equals Ri plus 1, Ti equals Ti plus 1, and then store back. So, R of Ri comma colon equals, so the alignment needs to change here again. So, I pushed it, I did the subtraction correctly, and then I shifted it so that I got the row alignment done. Now, I have to do the inverse of the shift, is that right? So, think about that. So, I have to reverse the shift and then align it and store it in R. Okay. So, R itself needs the alignment. So, I need to do a mul shift of R of T reg of Ti comma colon, right, with Z minus B of LIR comma CYL. Okay. So, this is the inverse of the rotation, and that gets stored in R. Once you have stored this in R, the L process is quite okay. So, we can go and do a cut and paste here. We do not have to do the whole typing, because plus, that is it. Okay. So, I think I have come to the end of the iteration over every layer. I think I am doing everything here. We will try it out and see if I have made any mistakes here. So, the total belief is stored there, you have the iteration number, and you have Ri, which counts the storage, and then I go through and do the subtraction, and then the alignment, I store it in the temporary thing. I then run through Minsum on the temporary thing, and then I column align again. But remember, I have to do this adjustment on Ri. I have to go back to the original index in my storage and then store it back. I think I am doing okay here. Okay. So, this looks fine to me. I have done the column alignment here. Okay, and then I have added it to L, and we are good to continue. So, once I am done with this, I have done my first layer. The layer is over. I have done all 3 operations on the layer. Once all the layers are over, the iteration itself is complete. Okay. So, now when the iteration is complete, I have to do message cap. Okay. So, I have to make decisions. So, how do I make decisions? We know how to do this. Message cap is L of 1 colon k, right. The first k bits are the message bits, and if they are less than 0, it is 1. If they are greater than 0, it is -1. Okay. And that is the end of the iteration. And once the iterations are done, you come out and check if message is not equal to message cap. Okay. So, that was the coding. Hopefully, you saw the various things that I was doing. I am definitely not claiming that this is the most efficient way to code up your LDPC decoder. I am sure there are much better ways to code it, and if you are not interested in seeing how I was doing the coding, you do not have to see it also. You can see the final code, it is available. So, let me just go through this code once just the way I have written it, and we'll try it out. I mean, I have to debug this, which will be another lecture, but let me show the overall idea and how I have done that. So, you load the base matrix, take its size and look at the expansion factor. Number of non-minus ones is important because that is the storage you need, and then temporary storage. So, there is some confusion about this R, okay, because that is the rate. Okay, did I redefine this as rate? Okay, so I will change this R as rate here. Does rate have any other role to play? Probably not. Okay, so rate is good. So, these are things to watch out for. If you reuse a variable, MATLAB will warn you. That is a nice thing to have. So, you can see that you are not making a mistake here. R is the storage for the row processing, Treg is the temporary storage, K is the number of message bits, NB minus MB into Z, N is the total number of code word bits, rate, and then you used rate to find EB over N0 and sigma, and then we are encoding the all 0 code word. Okay. So, that is something for simplicity, we are doing that for the decoder, it is not so crucial. We do BPSK modulation as before, and then add noise at standard deviation sigma. Okay. Now, it starts the soft decision iterative message passing layer decoding. You have your total belief L, which is very important. Based on that, you make decisions. My iteration number Ri, and I have an outer loop for iterations. For every iteration, you have to do this. We have to go through all the layers, and for every layer, you have to process all the columns. Okay. So, there are definitely much more efficient ways of doing these operations even in MATLAB, but I am just doing it laboriously to show you how it works. You go through every column, whenever you have a -1, you pull that value from the storage into the register, but you do this subtraction first. L is subtracted, and then you do a row alignment and store in the temporary register. So, the row alignment, once again, if you are confused about why I need the row alignment. So, if you see here, R is stored 1 to 16 in this sequence. So, this will be R of 1 comma 1, this will be R of 1 comma 2, and so on. Okay. So, this guy will actually be so this is 10. So, this will actually be in MATLAB's thing, it will be R of 1 comma 11. Okay. So, R of 1 comma 11 actually corresponds to the first row after expansion. So, R of 1 comma 1 is not the first row after expansion. After expansion, R of 1 comma 11 is the first row. So, I have to align it so that the first row matches throughout. So, I can just go through. So, that is the alignment operation here. So, you can see I have done the shifting by whatever value of B to get my correct value done. Okay. So, I am a little I think this is okay. Okay. So, I have subtracted, and that is the value I am storing into my storage register. Okay. So, that is good. And once I did that, I have to do minsum. Okay. So, and minsum I do it just on Treg, and this Ti I have kept count. This Ti is the number of non-minus ones in each row. Okay. So, when row is L by R, Ti keeps track of the number of non-minus ones. So, only the Ti by Z matter in Treg. There can be 19 rows, non-minus 1 entries in each row at most. So, I am keeping it as Ti by Z. Okay. And then I have this I1. So, I am processing the I1th expanded row. There are Z expanded rows in every block row. In the I1th row, I am processing one row after the other. I am going. I find the first minimum absolute value, right, in the I1th column, and then the second minimum in the absolute value. You also need the position of the first minimum, and leave out the first minimum position and find the second minimum, right. So, that is what I do here, and then all the signs, and then the product of the signs, parity. Okay. And then I assign the absolute value first after the minsum processing. For everything is min 1 except for the pos, which will be position of the min 1, which gets replaced by min 2. This is just an efficient way of doing it very quickly. And then the sign is assigned, right. So, you have to multiply with the sign. I used a dot into here because both of these are vectors, you have to do dot into. Okay. And then we are ready to do write back. Okay. So, for that you need column alignment again. Okay. So, you remember T-reg is row aligned and I have to make it column aligned. Okay. And when I have to make it column aligned, I have to do the reverse of the row alignment rotation that I did. Okay. So, I have here, so I am going back, this is reset the storage counter. Okay. So, we have come through to the end of the row, we have to go back, reset it and then do that, and then reset the counter for the non -1 entries, and then go through and increment Ri by 1, and this is my column alignment shift. So, you see instead of B of layer comma col, I am doing Z minus B of layer comma col, right. So, that is important to note. Okay. Okay. So, this is T-reg of Ti comma colon and then I add. Okay. So, I take the old values of L and then I add it to R of Ri comma I. So, I think this is correct. I think I have done everything correctly, but when we start debugging we will know if I made any mistake, a minor error or not. Maybe you caught some minor error I made. Once we finish debugging, we will have our code ready. Okay. So, remember, total belief is the actual final belief you have based on which you have to make a decision, and that is the decision here. Okay. So, it is easy to do. Okay. So, a lot of people would decide on the entire code word and use the parity check condition to see if the code word is valid or not and exit earlier than the maximum number of iterations. I have not done that here. I am just showing you the whole iterations. Maybe if you want, you can add that later on. So, that is why there is a while loop here. Okay. So, once you come out, after that everything is the same, right. What you did for the Hamming code you have to do here. You count the total number of errors. If there is any error at all, you increment the block errors by 1 and then the bit errors get added on to n bit errors. You find the bit rate, frame error rate and divide. Nothing changes there. Okay. So, hopefully, I mean, this is a little bit of a code. I mean, it is not very easy, it's but it is not that complicated either, right. So, the storage is what you have to manage carefully, and believe me, this is not the only way to do it. There are very, very efficient ways to write this code. In fact, you can write this code without any for loops. Okay. So, you can write it very efficiently in MATLAB using MATLAB's sparse matrix structure. It is possible to do these things, but I am not doing all that right now. So, I am just, this is more pedantic in the sense I am just trying to explain how the operations go and focus on the operations as opposed to efficiency in coding. Okay. But still, we haven't debugged this yet, we will have to debug it and to see how it works. We will do that in the next lecture. Thank you very much.